Hey everybody, in this lecture, we're going to be talking about igneous rocks. That's going to be chapter 4 in the Marshak book, or chapter 3 if you're following along in the online book. So what are igneous rocks? They're formed by the solidifying or freezing of magma or lava, and most igneous rocks are broken into two different categories. They can either be extrusive or intrusive, and we're going to define those. Extrusive igneous rocks are when, let me move my face, okay. Extrusive igneous rocks are rocks that are formed by freezing of lava above ground, so anything outside of the volcano. This could be when it comes in contact with air or water, and this is usually after it has erupted or extruded. An example of this would be a pyroclastic debris or volcanic ash. And so the rocks that would be formed as a result of this really explosive volcano here on the right, those would be extrusive igneous rocks. Now, intrusive are rocks that are formed inside. Think inside intrusive, outside extrusive. So intrusive is formed by solidification of the lava or magma that's still inside the volcano. Most igneous rocks are intrusive. So in this diagram here, we can see that we have magma is flowing up from the asthenosphere and then creates this main vent. And as it continues to go up through the volcano, we get these secondary vents and secondary cones where you might have some of these other little offshoots here from the main vent. And as this cools and solidifies, this is where we would see those intrusive igneous rocks. So why do you think magma rises? How does magma come from inside the earth and get to a point where it's creating a volcano and creating this eruption? Well, magma rises because of buoyancy. We talked about convection in a previous lecture, and that has a lot to do with it as well. So the buoyancy drives the magma upward. And the less dense rock, like molten rock that's less dense than the surrounding solid rock, is what drives the magma to create this cycle. And also the overweighing or the weight of the overlying rock pushes downwards, and then it can also squeeze the magma upwards. So think about when you squeeze a warm marshmallow. So think about like if you're making s'mores or something, how soft it is. So like a marshmallow itself is quite gooey and soft, but think about when it's melted and warm at how oozy it can be. So think about how you apply pressure onto a marshmallow and how it oozes between your fingers or how it stretches. That's an example of how an overburden or overlying rock would push down on magma, and that would cause it to squeeze and move. So what do you think controls the speed of flow? Because some volcanoes are fast and some are slow. What do you think would be the driving factors of those changes? So viscosity is a number one thing here. So viscosity affects the speed with which the liquid moves. So think about the differences between molasses and water. Molasses is very viscous, and therefore it moves more slowly than water. So if you were to pour out a jar of molasses or maple syrup, it would flow more slowly than water. And viscosity of a given melt depends on temperature. It depends on the volatile content and the silica content. So the hotter it is, the less viscous it is. And so there's some components here that causes changes in viscosity. like the temperature and silica content. So when magma rises, it cools because the temperature of the Earth is much cooler at the surface than it is below. We talked about how pressure and temperature increases with depth. And if magma becomes trapped underground as an intrusive igneous rock, it slowly loses the heat from the surrounding wall. And once it drops below that temperature of it being plastic or soft to being hard, then it solidifies underground. If the magma reaches the Earth's surface and extrudes as lava, that would be an extrusive igneous rock. It cools because it comes in contact with the cooler air or water above. So the takeaway here is that igneous rocks are formed by the cooling effect of either inside or underground, or extrusively outside by the air or water. So there's a few factors that can control the cooling time of magma. First is the depth of the intrusion. So magma intruded deep in the crust is surrounded by typically hotter wall rock, and it cools more slowly than the magma that would be closer to the surface. So again, temperature increases with depth. So closer to the surface, it's cooler. The further down you are, the hotter it is. So intrusive rocks that are at further depth take a little bit longer to cool because there's still a lot of ambient heat. Okay, another factor of cooling time would be shape and size of a magma body. So heat escapes from a magma at an intrusion surface. So the greater the surface area for a given volume, the faster it cools. And third is the presence of circulating groundwater. Water passing through magma can absorb and carry away heat. So if you're close to a body of water, and that's going to cool down the magma very quickly. So here's an example of surface area and cooling. So the larger the ratio of the surface area to volume, the faster an intrusion cools. And the ratio depends on both size and shape. So of course, if you have a greater surface area, like a pancake, for example, there's going to be more contact with air or water. And of course, if it's smaller, that's going to cool a lot faster than a really large mass. So there's a correlation in trying to understand how quickly something cooled, and we can see that through the presence of crystals. So early formed minerals tend to be relatively mafic, so their growth preferentially removes iron and magnesium from the magma, and the remaining magma becomes more felsic. So these are all words that we're going to go over as we characterize igneous rocks. But the thing to take away from this is that we have these different crystals that are present within rock. And there's a correlation between having more mafic and more felsic crystals in an igneous rock. And we're going to define those later on. But there is a correlation between cooling and crystallization. So here's a diagram that shows that as temperature decreases, so here this would be an intrusive rock, and this is a large blob that cools slowly, and it's originally the melt is mafic, and then as the temperature decreases and after some of those minerals settle out, the remaining magma becomes more felsic. And this means, generally speaking, slightly darker colors, and more felsic we associate with lighter colors. And we're going to explain that throughout the lecture. Okay, so here's some extrusive igneous settings. So some volcanoes erupt, some flood down the flanks of volcano. Mafic lavas tend to have lower viscosity and spread in thin flows or sheets, versus like volatile, rich felsic lavas tend to erupt explosively and form thick ash and debris deposits. So here's some examples of that here on the right. So here we have a very volatile eruption. We have pyroclastic flow, and we have this big ash cloud. And that's quite a different type of extrusive event than this slow lava flow, where it's spreading into thin sheets here. And we have a few other examples of seeing the aftermath, seeing outcrop of igneous rocks. And so here you can see thick layers of tuff that are deposited. And then down below, you can see there's slight variations here in the hillside that are associated with pyroclastic debris or pyroclastic flows. So those are some examples of extrusive, and here are some examples of intrusive igneous settings. Intrusive igneous rocks are distinguished generally by their shape. We can see tabular intrusions or sheet intrusions are roughly planar and have fairly uniform thickness. Some examples of these would be a dike or sill. And there's another thing here called plutons, and those are blob-shaped intrusions that range in size from tens of meters to tens of kilometers. And a vast composite body of plutons is called a batholith. So maybe you've heard the word batholith before, because sometimes this is described as a region of where we see a large amount of plutons. So here's an example. We have an intrusive rock, and between the wall rock and the intrusive igneous rock here, we have a contact. And again, these are rocks that are cooled below ground intrusively. And these larger blob-shaped intrusions can accumulate over time. And this is where we get batholith. And so some exposures of the Sierra Nevada batholith are seen here in the Sierra Nevadas. So let's talk a little bit more about what dike intrusions are. So dike intrusions take place in regions where the crust is stretching horizontally. This is typically found in a rift zone. So as the magma is forced, it's forcing its way through vertical cracks in the wall. So a dike is where you have this intrusion that's forcing its way in a vertical sense. So over time, it's going to experience this. So the dikes fill the space formed when the crust undergoes horizontal stretching. So as things are being pulled apart, there's room for the dike intrusion to go vertically. And the opposite of that is a sill intrusion. And sill intrusions occur where the surface, near the surface, so that the pressure from the magma can push the rock above the sill upward, leading to vertical movement. And so sills intrude between layers, and this may cause uplift of the land surface. So again, if we have, so instead of having vertical intrusions, we're having horizontal intrusions. And so as you squeeze magma between layers, it's going to cause the overburden to uplift and to move. So the source of plutons as magma chambers originate where faulting breaks the crust. So as the intrusion increases, the magma can push into these cracks. And so you can see over time here how if you have a naturally fractured rock, how magma can force its way into these cracks. And here's an example of what that would look like. You can see here in a cartoon version of how magma would be able to just penetrate itself into these cracks, but you can actually see it here that there's a very clear distinction between the granite and the surrounding wall rock. Okay, so let's characterize igneous rocks. We have three major textures: crystalline, fragmental, and glassy. And you may not realize it, but many of the buildings, floors, and kitchen countertops are made of igneous rocks. And so it's part of our everyday use that you wouldn't necessarily think, oh, this countertop is very beautiful. It's an igneous rock. So such as granite. Granite is used because it's durable and beautiful. You might have granite in your countertops right now, and you can impress your friends by saying it's an igneous rock. Okay, so let's talk about texture first. Crystalline texture. So when a melt solidifies, minerals in some rocks grow and interlock like pieces of a jigsaw puzzle. And they interlock because the grains, they grow around each other, and when they come in contact and fill in irregular spaces that are formed earlier from those grains. And we have a way to describe how large those grains are. So a coarse-grained crystalline texture is called phaneritic, and a fine-grained crystalline texture is called aphanitic. And there's one level above called porphyritic rocks, have large crystals surrounded by a mass of fine crystals. So there are these different crystalline textures here. And here's an example of granite, and it has a crystalline texture. And this, I would say, is coarse-grained. Usually when we try to distinguish between fine-grained and coarse-grained is something that you can visibly see with your eye. You might actually be able to measure it. Fine-grained would be much smaller. And so, let me move my face. Here's a chart that we use to classify crystalline texture. So these can be based on the composition as well as the texture, which I just described. And this helps us define the different types of igneous rocks. So here's the grain size, like I was just describing for you before. We have fine and we have coarse. And these other words I had used previously in the lecture, these describe the composition. So we use words like felsic, intermediate, mafic, and ultramafic. And what this really does is these mean the composition. So generally when we say things like felsic, we're really looking at how majority of the minerals in that rock are quartz. Maybe you see a little bit of plagioclase. That's this orange-ish color here. And things like rocks that are ultramafic are very dark in color, and that's because they contain mostly olivine. Or when we say mafic, has quite a bit of olivine, but also pyroxene and just a little bit of plagioclase. So all of these different words here that we use are related to the composition of the rock. Okay, so we talk about fragmental texture. This is formed from pyroclastic debris and consists of chunks or shards that are packed together. They can also be welded together or cemented after they have solidified. An example of this is tuff, and you can see how it has these larger chunks right here that are then forced together or cemented together after it has been solidified. So the surrounding rock that is cemented with these chunks looks a little bit different from the chunks themselves. And this is what we would describe as a fragmental texture. It's not uniform. It's where things are just packed together and fragmented. Next is glassy texture. It says made of a solid mass of glass or of tiny crystals surrounded by glass. Typically, they fracture in a conchoidally way, or like a clamshell, or it has a roundness to it, like a concave fracture, naturally fractured. And so this is an example of obsidian. Obsidian has also been used by native peoples to create arrowheads and things like that. So maybe you've seen obsidian before. And this would have a glassy texture. Okay, so when we talk about all the different types of rocks, there's a series of YouTube videos that do a great job of showing examples of these rocks. And accompanying these videos is a handy worksheet that's going to help you classify the different types of rocks. So I want you to use this worksheet and fill it out as you watch the YouTube videos. And so here's this worksheet. The link will be provided to you in Canvas. And this is the worksheet that you're going to use to classify igneous, sedimentary, and metamorphic rocks. So I encourage you to use this as you watch the YouTube videos.
All right, in this video, we're going to talk about igneous rocks. But before we can get into that, we have to step back a little bit. We're going to be using our flowchart from class, and we're going to be filling this out as we go. So let's get started. Now, we began this unit by studying minerals. And of course, we know that minerals are the building blocks of rocks. They are what make up rocks. So we know all about minerals and their characteristics. And so we're going to look at what happens when minerals combine in nature to form rocks. But this brings up another question. There are so many kinds of rocks, like this sandstone and granite, this piece of gneiss, this piece of obsidian, and shale and pumice. All of these rocks exist in nature, of course, along with thousands of other varieties. And so the question arises, well, how do we classify them? Do we group them by their color, their texture, their density? What do we do? Well, it turns out that the best way to classify rocks is based on how they form, the way in which they come to be. So let's add that to our sheet here. This bubble under the word rocks, we're going to write that they're classified based on their method of formation, or simply how they form. And so if you do this classification, you will have three categories: igneous rocks, which we'll talk about today, sedimentary rocks, and metamorphic rocks. And so let's take a look at igneous rocks. So what exactly is an igneous rock? An igneous rock is a rock that formed from the cooling and solidification of magma or lava. Okay, let's add that. So they form from the cooling and solidification of lava or magma. Now what that means is that when molten rock cools down and essentially turns into a solid, that is what an igneous rock is formed from. When you think of lava and magma, you probably picture this molten material in the crater of a volcano, and that's exactly what we're talking about. But what I want you to keep in mind is that there is a difference between lava and magma. When it's deep inside the earth, under the surface, we call it magma. Once it erupts onto the surface, we call it lava. Now, this material, whether inside the earth or on the surface, can cool and solidify, and so that gives us two different types of igneous rocks. Igneous rocks are classified according to where exactly they did their cooling and solidifying. And so we have two types. And let's start with the first type. The first type of igneous rock is called an intrusive igneous rock. That means it formed inside the earth from magma. Now, as you can imagine, it's pretty hot inside the earth, and so that magma is going to cool very slowly. So magma cools slowly. And when it solidifies, it will allow minerals to form in crystals. But because it happens so slowly, those crystals are able to grow very large. And so intrusive rocks are always going to have very large crystals. Let's take a look. This is a piece of granite, and what you'll notice is that it's speckled. All of these speckles are different mineral crystals. The black is biotite mica, the pink is potassium feldspar, the white is quartz. But the fact that you can actually see them with the naked eye tells me that they're big enough to have cooled slowly inside the earth, and that this is an intrusive rock. If you want to know what I mean by big, any crystals larger than 1 millimeter signify that the rock is intrusive. But of course, we can get really giant crystals like this pegmatite, where the crystals might actually be bigger than not a millimeter, but an actual centimeter. So we're talking about very large crystals here. So those are intrusive igneous rocks. But what about the second type? Well, as you might suspect, these are called extrusive igneous rocks. Instead of forming deep underground and cooling slowly from magma, these form on the surface. And because they cool really quickly from lava, you're going to get small or no crystals at all. And as a result, they may even have air bubbles trapped inside, which is something we call vesicular. So again, extrusive rocks form on the surface very quickly, and so you get very small or maybe even no crystals, and they may have air bubbles trapped inside. Let's take a look. This is a rock called basalt, and you'll notice that you can't really see any crystals at all. If you look with a magnifying glass, you would find really tiny ones that are smaller than a millimeter. That's a sign of an extrusive rock. What about this obsidian? Now this is interesting. It cooled so quickly in a matter of seconds that no crystals were able to form at all, and so you have this kind of glassy appearance. Finally, if it cools quickly enough, you might get air bubbles trapped in the lava and become part of the rock in the form of these vesicles or vesicular texture. You would look for air bubbles. So let's recap. A quick review. So igneous rocks form from cooled and solidified magma or lava. When it cools slowly inside the Earth, we get intrusive, sometimes called plutonic, igneous rocks, and they will have large crystals. When lava cools quickly at or near the surface, we'll get extrusive rocks, also called volcanic, that will have small or no crystals. They may be vesicular, meaning they have some trapped gas bubbles. Page 6 of the reference tables shows our common igneous rocks and their characteristics, and we'll be studying that chart in the coming days. Thanks.
So don't forget to fill out that sheet that's associated with this video because we're going to refer back to it for other lectures. So some of the things that the video pointed out is that igneous rocks form from cooled and solidified magma or lava. When magma cools slowly inside the Earth, we get intrusive igneous rocks. Typically, they have large crystals. And when lava cools quickly at or near the Earth's surface, we get extrusive igneous rocks. And generally, they have small or no crystals. These may be vesicular, meaning there are trapped gas bubbles. So these are some of the things that the video mentioned that the lecture didn't necessarily mention as well. So this is a great way for you to learn a little bit more through other resources online. So let's look at some igneous rocks in the wild. Okay, you move my face. There's no good place for my face. I'll just put it back here. Okay, so here's an example of an amphibole from Mount Whitney. So here we are generally where the star is, near the coast of Ventura County area, and Mount Whitney is the red triangle. And so the granite that forms Mount Whitney is part of the Sierra Nevada batholith. There's that word again. And in Cretaceous time, millions of years ago, the masses of molten rock that originated from the subduction zone rose underneath what is now Whitney and solidified underground to form large expanses of granite. So here's an example of granite from Mount Whitney. So if you're up this way near the Sierra Nevadas, you might see some of this granite. Granite is very abundant in the Sierra Nevada region. Okay, so here's another example. Again, here we are at the star. This is Panum Crater, so a little bit further north than where we are in Mount Whitney. I believe it's north, yes, a little bit further north. And so the Panum Crater is a volcanic cone that's part of the Mono Inyo craters, which is a chain of recent volcano cones south of Mono Lake and east of the Sierra Nevadas. Panum Crater is between 600 and 700 years old, and it exhibits all of the characteristics of a textbook rhyolitic lava dome. And here's an example of some obsidian that we see at Panum Crater. So if you've visited Mono Lake, this is not too far away. Okay, so here's one that's further south. Again, here we are. This is the Salton Buttes. This is near the border of California and Mexico. Further inland from San Diego, but along that way. The Salton Buttes are a group of volcanoes in Southern California on the Salton Sea, and they consist of 7 kilometers long of lava domes named Mullet Island, North Red Hill, Obsidian Butte, Rock Hill, and South Red Hill. So here, yeah, rhyolite. Okay, so here's an example of some of the features that you might see there. And this is an outcrop of some rhyolite at the Salton Buttes. So we spent a few lectures talking about plate tectonics. So how do you think igneous rocks and plate tectonics are related? What types of plate tectonic settings would you expect to see igneous rocks? So we can see igneous rocks at a few different boundaries. First, we see them at hot spots. We see them in subduction zones. We see them in mid-ocean ridges and in rifts. Again, so here's the map of all the different plates. And here are all of the volcanoes that exist around these plates. So you can see where there's volcanoes, that's where we get igneous rocks. So you can see here, especially in California, we have a lot of activity because of the plate boundary between the Pacific plate and the North American plate. But don't forget that we also see igneous rocks at hotspots like in Hawaii. So let's talk about hotspots. Again, this isn't a type of plate boundary. This is a special circumstance of plate tectonics. And hotspots occur where there's isolated points where a column of magma rises through the mantle, and this is called a mantle plume. Let me move my face again. And the plume reaches the base of the lithosphere to create this mafic magma. And in an oceanic setting like in Hawaii, usually this erupts as basalt. But we do see continental hotspots, and most of the time it's basalt. However, the crust partially melts and can produce felsic magmas as well. This would be an example of rhyolite. So the picture over here is the hotspots in Hawaii, and these are generally basaltic flows. So let's look at subduction zones. So a reminder, a subduction zone is where we have two plates converging together and one subducts under the other. This is a convergent boundary. So volcanic arcs can form in the overriding plate adjacent to the deep ocean trench. And this is where we have the convergent boundary right here. And subduction carries the crust down into the asthenosphere, and the crust warms and becomes hot that the volatiles separate. And so here we would have this volcanic arc, and you guessed it, this is where we would see igneous rocks. So in the continental volcanic arcs, not all mantle-derived basaltic magma rises to the surface, but some of it gets trapped at the base of the continental crust, and some of it resides in the magma chambers. So these would be some of those intrusive igneous rocks. As the magma rising up, it cools higher in the crust to form these plutons. And if it gets to the surface, then it erupts as lava. And some of the types of rocks that we see in these circumstances are granite, rhyolite, diorite, and andesite. So over here on the right-hand side is a picture of the igneous rock diorite. And you can see that it's mostly, it looks kind of like, Dalmatian-y. It's very polka dot, lots of white and lots of black and not any other colors in between. So what about mid-ocean ridges? This is where we have a divergent plate boundary, again, where we have two plates that are moving apart from each other. And this is where we see seafloor spreading, and where we see this, the spreading occurs where the asthenosphere can rise between the two plates, and it creates, it melts and generally creates new oceanic plate or continental plate, depending on where it occurs. So we have partial melting of the mantle, where we normally see peridotite, and this is a mafic magma, which rises into the crust and collects in the magma chamber. And as that magma cools, it can crack and form basaltic dikes. Remember, dikes are where we see the vertical intrusion. And that magma rises as far as the seafloor and extrudes as lava and forms pillow basalt flows. So as it's trying to reach the surface, it can extrude as lava or creates this billowy effect, and that's called the pillow basalt. And you can see that near the Bay Area. This is at Point Bonita in Golden Gate Recreational Area, and you can see that this is more like pillowy, billows as it's cooled quickly from the ocean water. Okay, what about rift zones? So rifts occur where there's horizontal stretching of continental lithosphere. As a result, the lithosphere is moved vertically. So partial melting due to decompression produces basaltic magma, which rises into the crust. And partial melting in the crust yields more of these like felsic, lighter colored, and they can erupt explosively as rhyolite. So a sequence of volcanic rocks in a rift generally includes things like lava flows of basalt and sometimes rhyolitic ash. And so here's an example of an outcrop where we see rhyolitic tuff as a result of an ash flow in the Columbia River. And again, these are where we see rifts of horizontal stretching. Okay, so large igneous provinces, this might be something that you'd see in the book, a term, LIP. So many places on Earth, there's massive quantities of mafic magma that have erupted or intruded, and they occur along the margins of continents, some on the interior of oceanic plates and some on the interior of continents. But these immense volumes of basalt are called large igneous provinces. And here's a map outlining the different regions where we have just large, vast amount of basalt. So this is where we see a lot of basalt, but it's not always exposed. And when I say things like when it's at the surface or it's an outcrop or something, that means that that rock has reached the surface to where we're able to view it. And so that means that it has been exposed to the surface. But a lot of these basaltic flows or really large igneous provinces are beneath our feet. And so this is where there's a large extent of igneous rocks beneath the surface. Okay, so to summarize what we learned this lecture, magma is liquid rock under the Earth's surface, and igneous rocks are formed by the solidifying or freezing of magma or lava. The melt viscosity depends on composition as well as temperature. We have two different types of igneous rocks, extrusive and intrusive. Magma occurs in different compositions. We talked about how there's a correlation between mineral content and the words that we use to describe those different compositions. So we use the words felsic, intermediate, mafic, and ultramafic. Igneous rocks are classified according to their texture and composition. Plate tectonic theory can explain why igneous rocks form where they do. We looked at some examples of different plate boundaries and where igneous rocks can be found. They can be found at hotspots, subduction zones, mid-ocean ridges, and rifts. So that's it for this lecture. See you next time.